Okay, so yeah, this is so yeah, what we want to do now is at least get an idea of Feynman's graphical method, see how it works. So this is something now called Feynman's theorem, but I'm not sure Feynman ever wrote it in this form. So we're going to write it in kind of Feynman's, people call it now Feynman's theorem. I think it's correct to call it like that because it captures the essence of his graphical calculus for computing integrals. I mean, in QFT, in quantum field theory, we apply the idea to path integrals or functional integrals, but the essence is here. I mean, that's so this is like, I think there's going to be several lectures. So the goal is to find an asymptotic expansion for, so we have an integral over Rn, something like, okay, my notation is going to be g of x, yes, e to the minus 1 over h bar, yeah, s of x dx. I mean, this is the nx, where, so this g could be any function, but for us is a polynomial function. In variable, g is a polynomial. But this s of x has a particular form. S of x is equal to basically minus 1/2 inner product of ax and x. There is this quadratic part. And then there is some gk over k factorial, some functions like, I don't know, I mean, maybe we just put in k of x, k bigger than or equal to 3, where these gk's are can be formal parameters or just constants. They're just coupling constants. We can think of them as formal parameters. This h is, or h bar, doesn't matter, is a parameter again, but keep it positive. And I better use negative here for this thing too. Okay. So that's what, so we know that this is going to be to have an expansion, asymptotic expansion. We already established this.
Also, there's one too many negatives. You have negative in front of 1 over s, then you have negative in front.
Oh, this should not be useful. Thank you. Yeah. Okay. Very good. Yeah, this should be positive. But if we keep this negative, then it saves us some trouble later on. Yeah. But it doesn't matter for this, but it's better. So we know that actually this guy, g of x, e to the minus 1 over h bar s of x dnx has an expansion of the form. What was the form of the expansion? That we derive, yeah, something like h bar to the power n over 2 times exponential of minus s of c over h bar, right? And then we had times a0 plus A1 H bar plus A2 H bar squared. There is such a, we know that such an expansion exists. So this is for at least as H bar goes to 0. But these coefficients A0, A1, A2, they are some combinatorial coefficients that can be written in terms of summing over graphs. That's what we want to do, and they're going to be functions of these coupling constants as well. So this asymptotic expansion is going to be valid as H bar goes to 0 or H bar small or 1 over H bar big. So are we okay with this so far? Okay, now what happens is that so let's look at a very simple case. Let's just look at a very simple case. So simple example. So let's take just a one-dimensional integral, something like integral over R, exponential of -1 over H bar, and then we have 1/2 A x squared plus G over 4 factorial x4 dx. Right? E to the -1 over H bar 1/2 AX. So this is exactly the one-dimensional version of this, where this matrix A is just this number A, and this A is positive, and there is this G4, we call it G. Okay, so to understand this, we can do change of variable. So we can change X to root H bar X. We can change variable to that, right? And then what we get? We get this is equal to, so dx goes to root H bar dx. So this you pick up H bar here. Here, of course, the critical point is C equal to 0. The minimum of this is at C equal to 0. And so this term, S of C is 0, so this term disappears. But it doesn't matter, we just look at it like this. So then this is times integral over R, exponential of -1/2 A x squared, right? And then I have got x4, so this becomes H2. You pick up the factor of H2 here. So we have got plus H bar squared over 4 factorial x4, and then there is dx. Yeah. So then this is dx. Okay, so now this, so far, this is an equality. But then to get the asymptotic expansion, the idea is to switch the quotient. Where? Here? Yeah. Why? I just took x to be, I changed it to my change of variable would be root H bar x, so that this cancels with this, with 1 over H bar here. And I have here H bar to the power n over 2, by the way. I also obtain it. So the thing is, this is the Jacobian of the change of variable, turns out to be in general. Yeah. Okay, so then what we do, this is equal to h bar 1/2 integral over r exponential of minus 1/2 x squared. And then this exponential of this guy, we just expand it. I just write it as sum times the sum of, yeah, these terms, h bar squared x4 over 4 factorial to the power, I'm going to use k index here, k divided by k factorial, k from 0 up to infinity. So far, everything is equality. There's no asymptotic expansion up to this point. It's just basic equality. Now we switch integration and summation, and then you get, we have to change this sign of equality to asymptotic expansion sign. And that's the fact that this is legit is a difficult theorem, which uses Watson's lemma. So this is asymptotically given by, so this is asymptotic expansion given by h bar 1/2 now sum k from 0 up to infinity integral exponential of minus 1/2 a x squared h bar squared x4 4 factorial to the power k divided by k factor. Yeah, so these are different terms of the asymptotic expansion. Okay, so in order to compute this, we have to compute such terms. Okay, so, and that's where Wick's theorem comes into the game. Okay. So then need Wick's theorem. So this Wick's theorem, simplest case again. Is the following: if you want to compute integral over Rn xij exponential of minus 1/2 ax x dx, and this I just put 1 over z0. This is equal to A inverse by j, where z0 is integral exponential of minus 1/2 ax x dx over Rn. But this Gaussian, we know what it is. This Gaussian is equal to determinant of root 2 pi over a, which I write it as also I can write it as 2 pi the power n over 2 divided by determinant of a square root of determinant. So this is this normalization or partition function for the Fourier theory. And this is the, so this quantity, sometimes people put it as xi, xj, and we call it the propagator. So this is the propagator. So this propagator is the matrix entry of the inverse of A. So in quantum field theory, you have this Laplacian, or you have your operator, then you have the green function. So matrix entries of the green function are propagators, but here is a very simple, very clear and clean justification to call this propagator. It gives you the inverse of the matrix. It solves the problem, propagates the problem. It's this. So this simplest case, this is the essential ingredient. And to prove this, so so to prove this, we introduced a quantity, we called it Z0 of J. We introduced a source term. J, so we had this thing called Z0 of J, which is integral over Rn, exponential of -1/2 AXX plus J dot X dn X. So J belongs to Rn again. It's a function of J. This function we can compute by using, by completing the square. We can compute this by computing the square. So this turns out to be equal to actually what it comes to. It comes to the following thing. Now, I would say it's comes to Z0 of 0 times exponential of 1/2 inner product of A inverse J and J. Yeah. Are you okay with this calculation? I mean, to check this, the easiest thing to do is to look at the one-dimensional case. So let's check the one-dimensional case again. The one-dimensional case is you're doing, so this is an example, this is a check, you're doing this e to the -1/2 x squared plus jx, right? dx over r. So this is equal to over r exponential of, now we can just write this as what? -1/2. Okay, so what can I do here? I mean, I can just say, all right, this is j squared. Okay. What to do with this?
Yeah, add and subtract the constant term you need.
We have to add and subtract the term, yes. So, but what term now? Okay, so let's factor this actually. I just factor it. Then I get x squared, right? And then this is minus 2j over a x, right? Yeah. This I believe is okay. And then I just have to add 4j squared over a2 and then minus.
I think it's j squared over a2, a squared.
Oh, j squared, yes, j squared over a2 and then minus j squared over a2, right?
Yeah.
Okay, so now this is equal to integral over r exponential of -1/2 a So this, I can write it as x minus j over a squared. And then I've got minus j squared over a2. So this we can write it as integral over r exponential of minus 1/2 a times x minus j over a squared. But then minus minus cancel times, there's a constant term which is independent of x. It comes out a minus 1/2 a inverse j squared, but minus minus is plus.
That matches up there, so good.
Okay, so yeah, this is the constant, but this by translation invariant of measure of this is the same as z0 of 0, right? That's the term that we have here. So this is so this matches this one. So this is correct. I mean, you have to do this for vector version of this completing the square, but that's easy. Okay, so this is it, and using this source term trick or generating function trick, now we can compute now. So okay, so what we wanted to show? We wanted to show that xi xj by definition equal to that. This is it, right? Okay. Yeah, this is at 0 of really 0, right? Basically. Okay, so if I then so what we have is that so what we're trying to say. So now what happens is that indeed 1 over z0 partial z0j partial ji partial jj becomes equal. This is indeed equal to xi xj. If you is that right? Yeah. If you look at this, when you partial derivative this with respect to xi and xj, ji and jj, you pick up coefficients xi xj in front. And then if you divide by this, you get exactly this term. So this implies that actually our xi xj is left-hand side, right? Is this one. So this is really like d dji d djj of this term, exponential of 1/2 a inverse j. But this term, if you look at it, it's a quadratic term with coefficients from a inverse. So this term, let's look at this term, 1/2 a inverse j, and j is sum. So this is like 1/2 sum a inverse ij ji jj. Now I'm putting this coefficient, so this is not good. Right? But the matrix A is positive symmetric matrix, right? And so this is symmetric matrix, and partial derivative with respect I and j picks up A inverse ij and A inverse ji, but they are the same, but divided by 1/2, you get exactly that. So this implies that indeed xi xj is equal to A inverse ij. So this is so Yeah, so that's the simplest case. Okay, now, but we can extend this, and that's what is called Wick's theorem, right? So let me write any question about this? Any extensions or any comments? Yeah, okay. So let's look at the general case then. So then Wick's theorem in general. It just says that integral x I1, x I2, x I m exponential of -1/2 ax x dnx over Rn is equal to 0 if m is odd, and is a sum of so it's a summation of the following terms. So yeah, I mean, let me write it in the following way. W of gamma, put it this way, over gamma. So this gamma belongs to, so if m is, for example, 2L, gamma belongs to labeled, so gamma belongs to the set of labeled one-valent graphs with 2L vertices. So this is the set. This is the set that we are summing over. We are summing over some certain set of graphs. These are one-valent graphs with 2L vertices. So imagine if L is equal to 1. So this is I1, I2. There's only one set of such things. If L is 2, you've got I1, I2, I3, I4. And in this case, how many? Oh, labeled. Labeled by this set of I1, I2, IMs. That's important to call it labeled. Yeah, because they don't have symmetries as a result. Once these objects are labeled, they don't have symmetries. So in this case, we have three such things. Okay, so I don't put these labels here. So this one, next one, and then the other one. So these are sometimes called pairings. So these are called pairings of 2L letters, 2L labels. Now, what I did not define is what is W of gamma, how the weight of a graph is, of such labeled graph is defined. To get this, we will decorate this graph with propagators. So in this case, we just put A inverse I1, I2. So if there's an edge, I mean it's paired, we just put A inverse I1, I2, and here we just put A inverse I1, I2, here is A inverse I3, I4, and here is again A I1, I2, I3, I4. This is A inverse I1, I3. This is A inverse I2, I4, etc. Okay, so now we have to be careful. We have to be careful. I did not divide here. I have to divide by this. So 1 over z0 again. Yes. I mean this we called it xi1, xi, right? We call this xi. So example. Of course, so something like xi1, xi2, xi3, xi4 is going to be equal to it's going to be sum of 3 terms. So it's going to be A inverse I1, I2, A inverse I3, I4, plus A inverse I1, I3, A inverse I2, I4, plus A inverse I1, I4, times A inverse I2, I3. So now, so this will have 2L minus 1 double factorial pairings. So number of labeled one-valent graphs with 2L vertices. So number of such things obviously is going to be, if you count, you see that you have 2L minus 1 choices for the first things to connect, and then 2L minus 3 and so on. So it's a product of all these things, 2L minus 1, 2L minus 3, 5, 3, 1, which we denote it as 2L minus 1 double factorial. So in this case, we have for 4, we have 3 terms, but for 6, we will have 15 terms. So now to prove this, you have to use some careful argument. Actually, we did the proof later on, and actually there's also a video that there's I gave you. Also, this is nicely connected to a version of Wick's theorem when you use creation and annihilation operators for that. That's in this where you apply this to canonical quantization rather than path integral quantization. So there is a version using this is called Wick ordering. It tells you that how you can write things in. It's actually normal ordering. How you can write things in normal ordering using Wick. It's a bit more complicated actually in that case, and it's kind of it doesn't look like this at all for A and A star, A n and A n star operators for creation and annihilation operator. But there's a Wick theorem there, which is equally well used. So, and that's in the video that I made. Question? Okay, so this we know. Then the case that I wanted to maybe look at simple case would be so one more example, integral x to n e to the minus 1/2 a x squared dx. So what is that? Can you say what's this? Yeah, or R.
Divided by, sorry.
Yeah, we have to divide by that thing, which is divided by 1 over, yeah, multiplied by 1 over z0. Well, z0 in this case, of course, is integral e to the minus 1/2 x squared dx, which is root 2 pi over a, right? So what is this quantity now?
2L minus 1 double.
2n minus 1 double factorial, right? That's just 2n minus 1 double factorial. I mean, yeah, we have 2n minus 1 double factorial pairings. This is x, 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 right? This is equal to x, 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 x. But the thing is, all weightings are the same. So
It should be a factor of A also on the right hand side. Or if you said A is equal to 1, then
oh, yes, yes, yes. There should be a factor of A inverse.
yeah, A inverse, yeah.
Very good. So we should have A inverse to what power?
The number of pairs, so I guess it would be L. That's my guess.
Yeah,
The L pairs.
half of the things, yeah. So it should be A inverse, but yes, A inverse to the power, yes. Or to the n.
Oh yeah, these.
Yeah, yeah, yeah. Because yeah, indeed, when we computed this, we got that. We got those terms. Yeah. But here I'm a bit worried because we divided here. Is that correct? Actually,
Well, Wick's theorem says you have to divide by that, right?
that's expectation value.
That's expectation value. So at least based on like.
So I agree, you get 2n minus 1 double factorial pairings, but shouldn't the power be just 2 because you're taking A inverse times B inverse
Oh
and
yeah,
adding it together n times?
yeah, that's right. I think it's just A inverse 2.
Should be A inverse 2 to the power 2.
I think so. I mean,
Really?
just using
Yeah,
the
this-
previous formula.
Yeah, I think Jamie is right because each parent.
Because if you write that out,
Oh,
it's
wait.
gonna be
No, I don't think so.
No, it can't be A inverse 2.
Because if you think like you have each block, each term is gonna be the product of n pairs. So you're gonna get an A inverse each time, and then you're adding all those blocks. So I think it is actually A inverse to the n.
No, it should be A inverse to the power n. You see, the propagator in this case is A inverse, right? For example, for this one. You decorate this by A inverse, A inverse, A inverse.
Oh, yeah, it should definitely be in. I see, I was just using the example from.
Oh, the example is is a special
Simple,
case.
yeah.
It's
Yeah, I
the
was
simple.
looking at the one.
Yeah, example for n equal to 4. Yeah,
Yeah, it's definitely in.
yeah. That's so simple. It's confusing.
Yeah.
Yes. Okay, so that's where we are. That's yes. So now what we want to do, we want to look at some more general results. Okay. Yes. Okay. So now we want to actually see how to turn this into summing over. Okay, so this is Wick's theorem now. So let's go back to our original problem. We wanted to compute this integral, asymptotic expansion of the integral exponential of minus 1/2 x squared plus g over 4 factorial x4 dx. I should not forget this h. I want to keep track of h actually. So let's put 1 over h bar here. This is better. Yes.
With a minus.
There's minus sign.
Oh, sorry, yeah.
Yeah, no, that's good. There's minus sign, minus 1 over h bar, and this and that. Okay, so let's now look at that. Okay, so this now is equal to, as we wrote, this is h bar half. So asymptotically is h bar half sum k from 0 up to infinity integral. Yes, exponential of minus 1/2 a x squared times, then we have got g, what was it, h bar squared, was it?
Yes.
H bar squared divided by 4 factorial to the power k x of g h bar squared x4, sorry, divided by 4 factorial, okay, yes, the power k divided by k factorial times dx. This is it, right? So this is the asymptotic expansion. So now this we can just write it as equal to h bar half. Okay, now this term, oh, this is 4. So so what is this term, this each individual term? So we have got integral e to the minus 1/2 x squared. This term is g to the power k. This term is g to the power k times g to the power k, h bar to the power 2k, h bar to the power 2k, x to the power 4k, right? Divided by 4 factorial to the power k times k factorial dx. Huh? Okay, so now the factors are like this. So this is equal to g to the power k, h bar to the power 2k, divided by 4 factorial to the power k times k factorial. Now, okay, so this coefficients we taken care of for now. And this times that, this is just z0 times expectation value of x to the power 4k, right? X to the power 4k. Okay. Now, of course, we know the value of this x to the power 4k in this case. It's just, yeah, it's just 4k minus 1 double factorial. But we can also see it as using, we can also think of it using Wick's theorem, original Wick's theorem. So you don't want to use this calculation. You want to use the graph interpretation. Okay, so this So now the idea now is write it as a sum over labeled graphs. Okay, so and what we do, so now here is the idea. Here's the main idea. I think I can erase this, all this here. This this term 4 factorial suggests we think of this coefficient, this number in the following way. So we've got 4, group of 4, and so let's assume k is, for example, equal to 3 now. Okay, so then I have another group of 4, right? So and this is the number of pairings of this two, in this case 4 times 3, 12 labeled vertices is the number of such pairings. But it now okay, so now what we can do, we can attach one vertex to each of these things, and then another vertex to this one, and then another vertex. So when you do now the pairings, like something like this, so imagine you do this pairing, for example. Imagine you do the following pairings, for example. Okay. So each of these pairings gives us a number. Now, let's see what we get here. So this ends us with what? This ends, we end up with a graph with 3 vertices, and each vertex has a 4 valency. So we get with 4-valent graph with 3 vertices. So 4-valent graph with 3 vertices. Okay, so let's draw some of them, right? For example, I mean, the simplest case is this, right? So you just get this obviously is obtained when you do pairings, not like this. You're not connecting this group with that group. You're connecting this group within itself, and you're connecting this group within itself. You get such graphs. But then what happens is that you have many of these things. So, for example, in this case, you can get actually 3 such graphs in this case, because the number of pairings of this group of 4 vertices are going to be, yeah, there's several of them. So I have just written up to isomorphism of such things. So this is this the thing now. They could be something like this. This is a four-valent thing, and then something like that. Can you give me some more examples of such graphs?
You have two internal loops and then loop on each end.
Yes, so here is. You mean,
Yeah, and then two loops.
but these are the connected ones. So you get some connected ones. But this is not connected, and this is not connected. Can you give me some more examples?
If instead of the end ones being self-connected, they could connect again, so you get sort of like a triangle of two ends.
You mean like this? So something like this.
Yeah, yeah. That.
A man with glasses. Something.
You have like if you move the one version
Yeah.
down, you kind of get a triangle.
Sorry.
You could also think of it as like a triangle.
Yeah. Oh, this one you mean?
Yeah,
I see. Can you give me another example?
Connected, or it can be any.
Whatever. Whatever you come up is okay. Yeah.
We did the data one already, but yeah.
Yeah.
Definitely not all of them.
I don't think they're all of them. No.
They're just connected ones.
Okay.
You could, oh, I got another one.
Okay, you have another one? Okay, what
Yeah,
is it?
so you can have,
Okay. Yeah, okay.
you can have one internal loop. Like this, I'll just show you that.
So one internal loop?
Or like this.
Oh, you mean like this?
Here, I have a picture. Oh, that's cool too. Yeah, that's another one.
No. This
Oh, wait, no,
cannot be.
there's six there,
This
yeah.
cannot be.
And then, yeah. I mean that.
No, this is not good. Well, maybe this one.
Yeah, that looks like a different one to me. It seems.
Is that a different one compared to this?
Yeah.
It looks like it, but yeah, maybe.
I think so.
Is that?
Because, yeah, you have like in that one you have two. I think it's two, but
Yeah.
this
Okay.
is the one I was thinking. Another disconnected one.
So which one? So you have two.
So you just have this.
Oh, yeah,
figure eight as the one disconnected part.
So you have this, yes. Okay.
And then
Okay.
you
So
have-
this. Okay. So this is another one, and then you have.
Connected.
Yes.
Middle and then two external loops.
Yeah. Exactly.
I think those are all the disconnected ones you can get actually because I think those are the only ones you can draw for
I see.
two vertices.
That last one you drew is the one for the thing over here.
That one
Yeah,
is which one?
the one for the original thing.
Oh, is that right?
I think so.
Yeah. Okay.
Yeah, it is. Yeah, you're right. That is the original one.
Right. Cool. Okay. Yeah. Very good. So now you see, we are changing the game now. We are not really using. We are not evaluating it directly, which in this case is easy because we are in one-dimensional case. But we want to do it in such a way that it carries to n-dimensional case, and that's the way to carry it to the n-dimensional case. So now, okay. So the trick is now to write summation over one-valent labeled graphs, turn it into summation over genuine graphs. Okay, so the trick now is the following. So the main idea now is the following. Because by Wick's theorem, we know that all these integrals can be summed, can be written as summation over labeled one-valent graphs, but that's boring and that's very tedious and that's not effective. So turn summation over one-valent labeled graphs into summation over graphs with okay, so let me put it like this, four-valent graphs with three vertices. I got K, where is, okay. Okay, it, yeah. So with K vertices. For K equal to 0, 1, 2, 3. Yeah. So we want to turn this Wick's summation, which is over one-valent boring pairings, basically graphs, into summation over graph, four-valent graphs with K vertices, where K is controlled by this number, this parameter. Okay, so then the result now is going to be like this. So this is the claim that we have to prove. Let me write the claim and then let's see how to prove it. In this case, at least, yeah, 1 over z0, I would say still z0 integral exponential equal to or exponential minus 1/2 x squared plus. Okay, now there is this business with h bar. We have to be very, very careful. Okay, so we'll carry that, yeah. Times, okay, that's okay. Plus, yeah, so again, let me put it like this. Minus 1 over h bar times 1/2 x squared minus g over 4 factorial x4 dx, right? This is okay, right? This one. So this is equal to root h bar sum f of gamma with gamma. Okay, so what's the gamma belonging to G for K? Yes, where E for K is the set of isomorphism classes of graphs, of four-valent graphs, four-valent. Well, valency, you know what I mean, right? Valency is the number of edges that that come to each vertex. I don't know, they're like called regular graphs of.
These are four regular graphs.
Four regular graphs, they're called also. Except that, I mean, in this case, they're counted as two. So
Okay.
there is a little bit of
Yeah, maybe valence better than.
valency. Yeah, they are not regular. Yeah, they are not.
Yeah, yeah.
Valency is the terminology. Yeah. So four valent. So let me put it like this: four valent graphs with k vertices, and this is summation k from 0 to infinity, by the way. Yeah, so we have two summation, k from 0 up to infinity. The interior summation is finite. And okay, so now what is that f of gamma? So this f of gamma is called Feynman weight of this graph. Of gamma, and it's defined to be the following. What we do, we will just decorate these graphs with propagators. So on each vertex, we are going to put a term G here, a G here, a G here. And then on each edge, we put A inverse. And then we multiply all of them. Okay, so yeah. And then we have to divide by the number of automorphism groups of this graph. So this is equal to, yeah. So I don't know, I don't want to write it down because, so this is 1 over order of automorphisms of gamma. We have to divide by the order of automorphism group of this. And then, okay, so we decorate each graph in the following way. On each vertex, we put this G, the coupling constant, and on each edge, we put the propagator. In this case, it's very simple, it's A inverse, and we multiply all of them. In this case, for example, it's going to be G3, and then A inverse to the power A inverse to the power 6. Divided by the order of the automorphism. Gamma. So we have to compute the automorphisms. And there is a factor of H, which we should not forget. There is some H bar to some factor. So we have to figure out this factor now.
Should be 2K, right?
The factor in this case, yeah, I believe is so because when we did change of variables, here came x4 because it became h bar squared, and then yeah, that's 2k. Yeah. So this is like the factor is like h2k in this case, right? The factor is h2k, right? Okay, so you see, even in this case, in this very simple one-dimensional case, there is something to be proved. It's not obvious because that summation and this summation are so different. So just why this is the case, I will prove it in the next lecture. Right now, I have to leave soon. So But yeah, so but that's the prototype of Feynman's theorem. So we'll go into n dimensions and then to infinite dimensions, and for matrix integrals takes a different form, but this is the idea. And yeah, so we have to think of this as kind of prototype of what we do. Any questions? Or I mean, the simplest case, for example, let's look at one simple case. For example, imagine k is equal to 2. So this would be graphs with 2 vertices. So 4-valent graphs with 2 vertices. So what are they? Just you want to draw some of them. 4-valent graphs with 2 vertices. I mean, obviously we always have this. That's one case, and then we can have theta graph. We can also have I don't know the total number of such things, actually. I don't know the formula, so there must be. If there is a formula, I believe there must be a formula.
For the number for each k?
Yeah.
We did that. It's just 2k minus 1 double factorial, right? It could be, in this case, in general.
No. These are for 1-valent graphs. We are working, in this case, you're shrinking a lot of things.
Isn't this set of graphs and bijection was the other set of graphs?
No, that's the whole thing. No, they're not. The other one were boring graphs, actually. We're just 1-valent graphs. They're pairings.
Yeah.
Now we change the problem. I mean, that's the whole thing. I mean, so my question is, what is the size of G4K? That's a difficult problem. Definitely.
But can't we just, okay, but maybe we talk about it after you're done.
Yeah, sure. So you have comment, Jim? Okay, so now it's a good point to stop, actually, because we reached the point where it's something we can discuss maybe. Okay, so I just finished now. Okay.